Great. So, hi everyone. My name is Sylvester. I'm going to present an overview of the Engineering Center. I'm going to walk you through all of the points. So the visual concept, we already have this view from previous presentations. Yeah, the structure of the engineering center will be divided into 3 floors and inflatable structure. I'll talk about those things later. Here is design proposed in previous mission, external design. We can see engineering center connected to power station, sanitation center, greenhouse. Here is the 3 floors and the 3 floor structure. One of the biggest challenges when it comes to creating settlements on other planets is building a safe place to live, whether it's on Mars or on the Moon. Space settlers will have to live, work, and sleep in an environment of extreme temperatures without oxygen, while being bombarded with radiation and micrometeorites. So there are quite a few existing designs of habits. One I like and I see potential in is some type of underground habitat, and the one we see is proposed by Redworks, adapted from construction principles of ancient cultures, such as pit houses and pueblos, as well as natural constructs like the shell of the Nautilus. So, although it's impossible to gather direct information on the interior of Martian and lunar lava tube candidates, scientists have the possibility to investigate their surface expression through the analysis of collapses and skylight morphology. Morphometry and the arrangement, and compare these findings with terrestrial analogs. So the structure you can see on the slide, it could be built upwards from the base of its excavation pit, with multiple levels organized around the central support shaft. Also, both Mars and lunar caves are as large as entire towns and could provide shelter for human exploration. That's one of the hypotheses. So caverns on the Moon and Mars can offer enough space, protection against cosmic radiation, and stable temperatures for astronaut bases. Researchers compared hundreds of underground formations on Earth, the Moon, and Mars, while on our planet, the diameter of lava tunnels typically ranges from 10 to 30 meters. Some of these features could reach more than 800 meters in diameter under the surface of the Moon and Mars as well, enough space to host a human colony. So lava tubes on Mars and the Moon turned out to be 100 to 1,000 times larger than those on Earth. Moving forward, researchers and designers in previous missions proposed several different internal designs. That's one example here, where we have very nice structure. Different sections on each floor. Then there's another one which is also very interesting. But in general, inner space design of the infrastructure is very much essential, and it should be 3D printed. Their internal design might have 8 feet in diameter, and they should be vertically sitting on the dusty and rocky surface of Mars. So habitats would have 3 floors with spiral staircases inside. That's what we had in previous missions as well. Sealed hatch for entering and exiting the pod in a spacesuit in the ground floor. Kitchen and plant garden at a higher level, and sleeping quarters would be included. So interior design should be quite spacious, light, and comfortable as much as possible. Each floor should have at least one window, if that's possible, covering the full 360-degree panorama, but should keep the crew from harmful solar and cosmic radiation. So astronauts can use the mobility chassis called a chariot without a pressurized cabin by riding in rotating turrets. They might wear spacesuits while driving these types of vehicles. At least 2 vehicles should be present for the extravehicular activities, such as collecting and bringing the ice and minerals. Also, there should be a garage on the ground floor to supply mining and water treatment to the crew. This is the first division here, which you can see on this floor. That's the ground floor of the engineering facility area, and that's the main area of the engineering workshop. It includes the 3D printing area, where printing design is integrated. It also has a spacesuit dust removing area where dust is removed mechanically and then magnetically from the spacesuit of astronauts when they come back. There is an engineering workshop maintenance with having a garage for supplies and collection of minerals and ice. A washroom is attached to the engineering workshop. There is an upwards spiral stair for going to the next floor, which you can also see here. Moving forward, we have first floor that it's called here. It's called data communication cultivation area, but this next floor is actually very important as well. It includes the kitchen to make and preserve food. Also, it has molecular biology and bioinformatics labs to test the food. Cultivation areas have the most food micro production system to preserve the food. Data and communication center is actually making the connection to the whole station and Earth, ground station on Earth. It also uses to make the reports and design of the whole project. An upward stair is used to go to the next floor. Then here is the next floor, living and entertainment area. This floor, last floor, is actually the kind of living area with having some social activities arrangements. It includes the bedroom, social and entertainment area. Also kitchen, washrooms, and a medical health area. The medical health area has an ICU and isolation room for critical patients. It might look like this. That's another design. Moving forward to applied technologies. This actually that's a quite big topic. We might have lots of different things, starting with some things we already tested. So Mars missions are a chain of innovation with modern and innovative proven technologies, and scientists and astronomers have found new possibilities for great exploration, like the MOXIE instrument located inside the rover's body and convert the CO2 into oxygen's Martian atmosphere. We might kind of adopt and integrate some type of device like that in Martian habitat. The Ingenuity Mars helicopter is a small autonomous rotorcraft to test powered flight in the thin Martian atmosphere. One of the great machines and technologies, entry, descent, and landing technologies, including the range trigger, giving the parachute precise timing. Range trigger technology shrinks the rover's landing ellipse and allows it to land closer to the target area with great accuracy. Another technology is terrain relative navigation, which helps to avoid hazardous terrain. Another technology, interesting technology is the advanced aerosol sensor package, which helps record what the spacecraft has experienced during its landing and performance. The entering area comprises two main dust removing technologies that remove the dust from astronaut suits when they came back. The first comprises the brush rollers that remove the dust mechanically and drop it over the floor. The second part includes the mini platform, which use dust magnetic property to gather it in the bag. But starting easy, or also talking more about the habit, there are lots of different things. For continuous communication between Earth and Mars, potential data relay satellites are required, as all the communication from Earth will be done through satellites. Then, obviously, environmental control and life support systems, heating, ventilating, and air conditioning systems, and many other things. This is, one of the concepts here of the systems. This concept here presents dust removal. It's a dust removal system or mechanism proposed in previous missions, in one of the previous missions. This part here, that's something, what's quite interesting for me personally. When we have dirt or dust on any heavenly, body is commonly referred to as regolith. It's most often just volcanic rock that has been crushed or weathered over time into a fine powder. And, on Mars, beneath a layer of rusting iron minerals that gives the planet its famous reddish hue, like a thicker layer of silicates with names like pyroxene, feldspar, olivine, which are made up of silicon and oxygen structures bonded to metals like iron, aluminum, and magnesium. And now, excavating this material is challenging because its consistency and compactness varies from place to place on Mars. But what makes the task even harder is the planet's low gravity, which makes it difficult to push a shovel into the ground without using your weight to counteract that force. On Earth, when we dig dirt, we often use large vehicles because their heavy bodies react appropriately to the forces of the much smaller digging bucket. But remember the gear ratio problem. Every once that we launch to Mars is precious and very costly. So we had to figure out a way to dig on the surface of Mars using lightweight equipment. Most likely, we'll use excavating robots on Mars. You can see one of the designs, NASA designs, here on this slide. Most probably those robots will go there long before humans ever set foot on the planet. To test its excavating robots, NASA uses an enclosed facility with more than 100 metric tons of crushed volcanic rock. The material serves as an analog for the extremely fine and abrasive dirt particles found on the surface of Mars. Moving forward, we have management. So organizational structure, starting easy and small, we might have engineering center chief. That person would be responsible for studying how the in situ practices are going on, monitoring each and every section of engineering center, things like workshop, rover maintenance, data center. Also will be contacting directly ground stations on Earth and other facilities as well. Doing some type of daily inspections, direct communication, with other centers, like I mentioned before, monitoring all of the protocols, all of the things like that. Then we have technicians, most likely responsible for spacesuits related activities, things like 3D printing processes and maintenance of equipment, including rovers, antennas, and those kind of things. Then we have assistants. In this situation or in this role, they will work under the chief as well, responsible for some type of stack management, and can be conducted in case any tool or equipment is required. In this role, I included visitants, so I would like to have just one crew member staying there for a while and coming from different sections. So one of the responsibilities or benefits would be that this person would bring some knowledge and also exchange knowledge with different centers. That might be quite interesting. So people can learn and exchange knowledge. But later on, this is just the type of start we have here. But later on, after the base grows, we might need a more complex structure, and our organizational structure might include the overall designing committee and their team members, which carry our projects and respective responsibilities, things like that. The main facility chief or committee head would have 3 different managers, including the engagement manager, project director or program director, then potentially some technical consultants. Or the project director might has its project manager and deputy project manager, consultant, technical consultants would be connected to all project managers. Moreover, the engagement manager might be connected to deputy project manager to have some development discussions regarding projects. But that's long-term vision, of course. Deputy manager might have 3 teams: the analysis and design team, technical team, and the implementation team. These all people collectively include the organizational structure that performs various tasks like building the habitat and its repairing and maintenance. They all collectively plan the extravehicular activities and the activities planned during the operation. All the assistants, researchers, technicians, and engineering chief must have engineering backgrounds like data science engineering, mechanical engineers, and astrobiologists. But we also need many other people like psychologists, people who can make food and things like that. But they must know all the engineering safety protocols, all of them. So moving forward, positions, astronaut profile, and duties. Like I mentioned here, there are various positions, not only the astronauts according to engineering facilities required on Mars, scientists, computer science engineers, researchers, and so on and so on. Profile of engineering center chief must have multidisciplinary with excellent management and industrial experience. That person should have high leadership capacity with great personal resilience. Its duties should be inspection and control of daily ongoing activities. The engineering center chief should be responsible for proposing routines and operational protocols with reports daily submission to the main station. Also, should design SOPs for the smooth functioning of the station while coordinating with other facilities. Like I mentioned before, researchers' profile should have engineering and science background with excellent research and development experience. Basically, problem solvers. Their duties include the development of new technologies and upgradation and improvement of existing technologies. Then again, to recap, technicians' profiles must be from an engineering and tech background, maintenance, activities experience, providing the services and managing all the site installation tasks, repair and maintenance, They also repair and charge the electric vehicles so that extravehicular activity can be performed. They are responsible for diagnosing the errors and technical problems during the flight and providing its proper solutions. Then we have, mentioned on this slide, IT or computer science engineers. They might have duties to make the design, installation, and maintenance of computer systems and things like that. They must troubleshoot, test, and configure the facilities, hardware, software, and other networking systems to meet the needs and expectations. For example, microbiologists should conduct complex research projects and improve sterilization procedures. Also, they develop new drugs to combat, fatal infectious diseases, and they also perform the duties of lab experiments to diagnose the illness and its better treatment. Moving forward, we have astronaut training program. So on this, in this topic, basic training, basic training is required for astronauts in that center, engineering center. The training related to dust removal system should be given to all of the astronaut members. Also, while working, keep in mind the sustainable use of space habitat as well as resources, support long-term effects of isolation, capabilities to handle the architectures, technologies for human exploration, and things like that. But the astronauts training program is, in general, should be well designed to develop the essential knowledge and skills required for formal mission training. Upon selection for a flight, they undergo a complete 2-3 years of training and evaluation period. They undergo different physical and emotional tests. They learn many things other than science, just like medical training in case of emergencies. They are trained to be able to cope with the challenging living environment on Mars. They also trained to study Mars geology and exobiology. The astronauts training program is actually it's a unique training program of working in microgravity, which presents its challenges. Training programs familiarize the astronauts with each complex and highly specialized flight vehicle, equipment and suit to simulate a microgravity working experiment. Also, environments with radiation and other problems like that, other challenges like this. It's just like an educational training program where different learning stages have been developed to train the astronauts for extravehicular activities. Moving forward, there are 3 YouTube videos. So, astronauts are usually trained through the design training program. During the training, they also get familiar with the working environment of Mars, or of lunar, for example, lunar environment. And here are 3 videos where you can see what kind of trainings they have or how they are trained. They get to know the space aircraft, for example, actual internal working operating system, and train through different teamwork projects and various extravehicular activities and many other things. Moving forward, so here we have a topic, resources needed for 1 week. Like I said, here to start easy, astronauts use water, oxygen, food for their survival on Mars. Moreover, it's not possible to send all of this from Earth. It will not be sustainable. Therefore, they must produce all of those or most of those on Mars. Water might be extracted from the soil, but there are, of course, a few other concepts as well. The landing of the rover is is selected based on the water availability in the soil. The live support units perform water extraction. Soil is deposited into a water extractor, which hits the soil, and water is evaporated. This evaporated water is condensed and then stored. Regarding the amount of water, there are many concepts or proposals. Some people say minimum 34 liters per week. I would go with at least 50 liters of water per astronaut for 1 week. Oxygen can be produced by splitting the water into its constituent parts. Therefore, oxygen can be used to provide in the living units. A portion of oxygen can be stored in reserve to be used when less power is available, and that's quite important too. Nitrogen can also be extracted directly from the Martian atmosphere by the life support unit. Food required for the astronaut. The astronauts can be transported and stored in a life support unit. However, the stored food from Earth can only be used as an emergency ration, I would say. So astronauts prefer to eat as much food as they can produce on Mars, but most likely no more than 2 kilograms per day. Food can be produced indoors under artificial lighting, as there is available soil for plant growth in the original habitat. A thick layer of Martian soil will protect the plant from radiation as well. Carbon dioxide is available through Mars atmosphere, and water is available through recycling of the water extraction process. A required volume of the soil is investigated and suggested in the simulation outpost to produce food. This aims to reduce the food that is transported from the Earth. So moving to the next slide. Okay, so we have guidelines to be provided to other facilities and whole station. Actually, that's another interesting topic. So there should be some basic guidelines provided to every crew member and should be followed strictly. We might have regular research and development activities in terms of required facilities so that the project completion should be successful. The chief of facilities staff should have daily routine meetings that discuss ongoing activities and projects to run smoothly without any problems. Here we have three type of guidelines. Let's start with the first one: emergency guidelines. Entire crew groups have been trained well and should be trained well to deal with emergencies. Every astronaut is informed about the project's integrated process and has been assigned with their respective tasks. Then the next one, health risks guidelines, might say that they are guided with various health risks and guided to survive in outer vacuum space travel. They all are well trained and well guided in the International Space Station about what they will do when they get there. And the last one, equipment and process risk guidelines. So they are guided on using the data reports and 3D printer for smooth running of projects. So optimum work distribution per floor is well informed and guided to the entire station so that any uncertainty on any floor can be well known on an immediate basis. So let's move to the next topic, and that was protocols. And here we have specific protocols, routines of the facility. I will give some kind of overview here because again, it's a quite large topic. specific routines and protocols of the facility are used and are most important during the operation. There must be maintained regular contact from the Earth via the DRS, which is a data relay satellite, so that the whole structure of the center should be monitored daily. The spacesuits which astronauts use must be dried of dust whenever they go out, and rover should be checked every time before use. So everything that is of daily use should be placed back in its position every time after the use. Data reports should be maintained and back up regularly. The machines like a rover, electric vehicles, and 3D printers should not be overloaded during the use. The facility must ensure this all specific routine protocols. So moving forward, we have protocols of safety. Also quite large topic. So first of all, there should be some safety protocols while working on a project or mission on Mars. So we should always have a daily routine environmental disinfection check and balance. Also, always go through the air chambers for cleaning purposes when astronauts come back from an external mission or interact at other centers. They must have a fire detection system and also a specific control system for it. The crew always has a backup power system in case power goes down. All the space crew members should have frequent hand disinfection. They should have an automated system for the environmental and components disinfection. Moreover, they have frequent simulations of emergencies. That's quite important from my point of view. Things like safety for extravehicular activities are. This is also necessary to avoid uncertainty, to ensure a safe landing, human and rover locomotion. There should be a 3-dimensional terrain morphology map of landing operation zones. At the landing site, the Martian regolith specific range of mechanical properties should be characterized effectively. Then the next thing might be, the different properties like regolith strength, stability, sinkage properties like bearing strength, yield strength, build modulus, and the internal friction angle should be determined within the situ experiment. Okay, so let's move forward. Then this topic is a bit easier or lighter. So protocol for occupancy entertainment. Like I say here on the slide, protocols for entertaining the astronauts and their occupancy should decrease the stress to have a cool and comfortable atmosphere. Social gatherings with smooth music inside the space habitat, every regular day would be a significant step towards decreasing the chances of depression while working in isolation. Potentially a small movie room having rest facilities with a complete music scene would be great. Also, the cultivation activities and social areas can be organized, and exercising activity would be fantastic, to keep them mentally and physically fit. Next slide. So protocols for food microproduction. Those protocols are extremely important to have a specific check and balance over food availability for the crew members. There is a microproduction floor where food is preserved. Therefore, food logistics must be regularly checked and calculated. Every crew member uses the available food according to need, and there should be a management system to recycle it. Also, every week, the risk management system should look at the available food, and necessary precautions should be maintained to avoid the extra losses of food items. On the left side, on the slide here on the left side top, you can see some type of concepts and designs. But then the first growth test of crops in the advanced plant habitat aboard the ISS, International Space Station, yielded those results, which you can see here or on the left top side. The name was of that plant is Arabidopsis sits, as far as I remember. Small flowering plants related to cabbage and mustard, and this plant grew for about 6 weeks and dwarf wheat for 5 weeks. Then on the right side, the big picture, it comes from NASA, from the crop food production research area of the space station processing facility at the Kennedy Space Center in Florida. So that's just one example of how it might look like. Moving forward, we have protocols for 3D printing. 3D printing protocols, are obviously valuable, but all astronauts should have check and balance over the printing waiting line. What that means, they should organize and decide a specific printing time. They should test the material and pay attention while making a progress report that shows all the amount of material used while working on a particular project and the amount of material left behind or available in the spacecraft or habitat. 3D printers should be maintained and should have routine checkups as per requirement. Moving forward, we have spin-offs, technologies, and outposts that could be applied to Earth. That's a really great topic, and I enjoy talking and writing about those things a lot. So like I say here, different useful technologies could be applied to Earth, and their outputs would be significant in terms of quality Mars missions, like this supercritical Brayton cycle technology in cold fire power generation. The Earth is one of the great technologies. Also, the waste material refilled 3D printer is the technology of Industry 4.0 on Earth. The dust removal systems, which is extremely interesting for me, from the technology and research perspective, can be very effective and productive technologies that can be used in car washing activities, the place where people are mining. These technologies and their output can be beneficial while being applied to Earth. Of course, there are lots of other examples and opportunities here. Moving forward, we have guidelines to be applied to daily life on Earth. There are many general and some specific guidelines that should be provided to daily life on Earth. These guidelines can be beneficial for the better assessment of the projects on Mars. But there should be much investment in the new projects, as the investment in research today will give a lot more comfort and betterment of the projects and research tomorrow. This is a great way to sustain life, as the new technologies and development in the industrial field are much more required. Also, waste management activities must be practiced regularly. Moving forward, impacts to sustainable development goals topic. Starting easy, like I say here, improvements in the infrastructure of the operating and developing new technologies will substantially impact sustainable development growth. But what's important is that these results will have a more significant effect on economic growth. It will help out to reduce the waste, reuse it, and recycle it. So therefore, the waste material recovery facility will be improved. Also, there will be no more energy consumption systems, as new technologies and development systems will be introduced to use less energy and be more efficient and environmentally friendly. Okay, and here I put some references, some links and documents. And that's it. Thank you very much.